Far out in the depths of space, almost 300 million light-years from our own Milky Way, lies a true titan of the cosmos. This is NGC 4889, a supergiant elliptical galaxy so immense it anchors the entire Coma Cluster, a sprawling metropolis of thousands of galaxies. If you could see it with your own eyes, it wouldn't appear as a delicate spiral, but as a colossal, ancient sphere of stars, a ghostly behemoth glowing with the combined light of over 10 trillion suns. But its sheer size is only the beginning of the mystery. What truly staggering secrets could be hidden within this island universe, a place that contains one of the largest supermassive black holes ever discovered? What happens in the heart of such a monster, where the laws of physics as we know them are stretched to their absolute breaking point? Today, we are embarking on a voyage to the very edge of known science to peel back the layers of this cosmic giant and confront the unknown. We will be diving deep into 30 of the most bizarre, perplexing, and downright strange phenomena that astronomers have observed within and around NGC 4889. This is not a tour of pretty pictures. This is an investigation into the cosmic anomalies that challenge our fundamental understanding of reality. We are talking about gravitational whispers that suggest matter behaving in ways it simply shouldn't, about regions of space that appear to be empty in a manner that defies explanation, and about energetic signatures that hint at processes we can only describe as exotic physics. This journey is about more than just cataloging curiosities. It is a testament to our own human drive to explore, to understand the universe not just as it is, but as it could be. Every strange flicker of light, every unexplained warp in space-time we uncover in this distant galaxy is a piece of a grander puzzle, one that speaks to the very fabric of existence. So prepare to have your perception of reality challenged. We are about to venture into a realm where the normal rules no longer apply, and where the discoveries we make might just redefine our place in the cosmos. Our first stop on this journey into the unknown brings us to the very heart of the galaxy itself, to a presence so overwhelming it dictates the fate of everything around it. Yet when we look closely, we find a profound and unsettling silence. Meet the central supermassive black hole of NGC 4889, a sleeping giant of almost incomprehensible scale. This is not just a large black hole, it is a cosmic titan with an event horizon, the point of no return, so vast that our entire solar system could comfortably fit inside it many times over. To put its 21 billion solar masses into perspective, the supermassive black hole at the center of our own Milky Way, Sagittarius A star, is a mere 4 million suns. The one in NGC 4889 is thousands of times more massive, a true leviathan. But here lies the central enigma. This behemoth is dormant. It is quiet. Billions of years ago, astronomers believed this black hole was a brilliant quasar, a blazing engine at the galaxy's core, feasting on unimaginable amounts of gas and dust. The energy released would have outshone the entire galaxy, a beacon visible across the universe. Today, that furious activity has ceased. The question of why is one of the most pressing in modern astrophysics. What could possibly cause a cosmic engine of this magnitude to simply switch off? The leading theory suggests a simple yet profound explanation. It has simply run out of food. After its epoch of violent feasting, the black hole may have consumed most of the available matter within its immediate gravitational reach. Without a steady inflow of gas to heat up and accelerate into a brilliant accretion disk, the engine has no fuel and the quasar goes dark. This dormancy, however, is not a sign of weakness but perhaps a mark of ultimate dominance. Its immense gravity has likely already structured its entire galactic neighborhood, clearing out the chaos and establishing a stable, ordered system. The very peace we observe might be the lasting legacy of its past fury. This state offers us a rare and valuable glimpse into a critical phase of galaxy evolution. It suggests that even the most active, violent hearts of galaxies can eventually settle into a quiet old age. The silence of this colossus is not an end, but a new chapter, one that raises even deeper questions about what might happen if or when this sleeping giant ever wakes up again. But if the silence at the galaxy's heart is profound, the true, invisible bulk of this cosmic titan lies not in its stars or its dormant black hole, but in a substance we cannot see at all. This brings us to the second, and perhaps even more fundamental, strange phenomenon: the ghostly halos of dark matter that provide the galaxy's true skeletal structure. While the stars of NGC 4889 form a brilliant, visible sphere, they are essentially just the decoration on an infinitely larger and more massive framework built from this mysterious material. We know dark matter is there not because we can photograph it. It emits no light whatsoever, but because of its overwhelming gravitational influence. The entire galaxy, from its core to its outermost fringes, is wrapped in an immense, unseen halo that holds everything together. The primary evidence for this comes from a technique known as gravitational lensing. The sheer mass of NGC 4889, concentrated in both its stars and its dark matter, warps the fabric of space-time around it. When light from even more distant galaxies passes by this gravitational well, its path is bent, much like light bending through a lens. By carefully measuring the distortion of these background galaxies, astronomers can essentially map the total mass distribution of the foreground galaxy. For NGC 4889, the results are startling. The map reveals a halo of mass that extends staggeringly far beyond the last visible star, a ghostly presence whose gravitational pull continues to dominate space for millions of light years. It is this immense, unseen grip that governs the motion of the galaxy's retinue of globular clusters and satellite dwarf galaxies, whipping them around on orbits that would be impossible if only the gravity from visible stars were at work. What makes the dark matter halo of this particular galaxy so strange, however, is how its properties challenge our best theoretical models. In many galaxies, dark matter seems to be concentrated in a specific way, denser in the center and thinning out toward the edges. But in a supergiant elliptical like NGC 4889, the distribution appears to be different. Its incredible stellar density and the aftermath of its ancient galactic mergers may have somehow altered the dark matter profile, making it either smoother or more diffuse than our simulations predict. This discrepancy is a crucial clue. It suggests that the nature of dark matter itself, whether it's a cold type of particle that moves slowly or a slightly warmer, more interactive one, can be tested by studying the most massive galaxies in the universe. The ghostly halo of NGC 4889 is not just an invisible scaffold. It is a natural laboratory, one whose very structure holds the key to understanding the most abundant form of matter in the cosmos. However, the invisible grip of dark matter is just one piece of the puzzle when it comes to the true nature of this galaxy. To understand the full picture, we have to look at the motion of the things we can see, the stars themselves. This leads us directly to our third strange phenomenon, a discovery that has left astronomers scratching their heads: the anomalous velocity dispersion of the stars within NGC 4889. In simple terms, velocity dispersion is a measure of how much the speeds of individual stars within a galaxy differ from one another. Think of it like a crowded freeway. In a well-ordered, calm galaxy, most stars will be moving at similar speeds, like cars all cruising steadily in the same direction. A low-velocity dispersion suggests a settled, relaxed system. But if you measured the traffic on that freeway and found some cars creeping along while others were zooming past at incredible, random speeds in all directions, you'd know something unusual was going on. That chaotic freeway is a good analogy for what we see in this galaxy. For a massive elliptical galaxy like this one, you would expect a certain amount of stellar hustle and bustle. Its immense gravity naturally pulls stars into fast, complex orbits, but the measured velocity dispersion in NGC 4889 is unexpectedly high, far beyond what its visible mass alone can account for. It's as if the stars are being stirred by some unseen, energetic force. So, what could be causing this stellar frenzy? Astronomers are investigating two leading and equally fascinating possibilities. The first theory points to a violent past, NGC 4889, as the dominant galaxy in its cluster, is likely a product of galactic cannibalism, having grown to its colossal size by consuming smaller neighbor galaxies over billions of years. It's possible that a major merger with another large galaxy occurred relatively recently in cosmic terms. If this is the case, the galaxy we see today may not have fully settled down from that colossal collision. The stars from the two merged galaxies would still be interacting, their orbits not yet circularized into a calm, orderly system. This would create a period of gravitational chaos, with stars slingshotting around on wildly different paths, resulting in the high-velocity dispersion we observe. It's the celestial equivalent of the waters in a pond remaining choppy long after a large stone has been thrown in. The second theory brings us back to the ghostly presence of dark matter. The immense dark matter halo we discussed earlier could be the primary driver of this stellar turbulence. The sheer amount of unseen mass concentrated in the halo creates a much deeper and more complex gravitational well than the stars alone would produce. Stars orbiting within this potent gravitational field are subjected to stronger and more varied pulls, accelerating them to higher speeds on more randomized trajectories. This explanation paints a picture of a galaxy whose visible stars are simply tracer particles, their frantic motions acting as a direct readout of the powerful, invisible dark matter engine that surrounds them. The high-velocity dispersion in this view is not a sign of recent turmoil but a permanent feature of a system dominated by an overwhelming amount of dark matter. Determining which of these scenarios is correct, or if it's a combination of both, is crucial. It tells us whether we are looking at a galaxy that is still dynamically young and recovering from a dramatic event, or one that has always been this way due to its fundamental construction. This anomalous measurement is more than just a curious statistic. It's a vital diagnostic tool. By studying the velocities of these ancient suns, we are essentially taking the temperature of the entire galaxy, gauging its history, its stability, and the true source of its immense power. The restless stars of NGC 4889 are sending us a clear message. This colossal system is anything but quiet and dead. It is a dynamic and perhaps still evolving cosmic beast. Yet, for all the frenetic motion of its stars, NGC 4889 presents us with a scene of profound and unexpected stillness when we search for the most fundamental sign of cosmic life. This brings us to our fourth strange phenomenon, the galaxy's bafflingly empty larder. In a universe where galaxies are often bustling factories for new stars, this colossal giant appears to be a ghost town of stellar birth. The essential ingredient for creating stars is called molecular gas, a dense, frigid clouds of hydrogen and other molecules that can collapse under their own gravity to ignite new suns. In many galaxies, including some other large ellipticals, astronomers can detect vast reservoirs of this raw material. But when they point their most sensitive radio telescopes toward NGC 4889, they find a startling void. The amount of cold gas is vanishingly small, far less than what should be present in a galaxy of such immense size and mass. It is a cosmic desert at the heart of a celestial oasis, a paradox that demands an explanation. How does a galaxy simply run out of the very stuff that built it? To understand the strangeness of this absence, it helps to contrast it with what we might normally expect. Our own Milky Way, a spiral galaxy, is still actively forming stars from its plentiful supply of gas. But even some aging elliptical galaxies, which are generally less active, often retain pockets of cold gas, sometimes acquired by cannibalizing smaller, gas-rich neighbors. The fact that NGC 4889, the most dominant galaxy in its entire cluster, a galaxy that has surely consumed many others, shows almost no trace of this material, is a powerful clue. It suggests that something far more forceful and efficient than simple aging has occurred here. The galaxy hasn't just gently used up its fuel, it has been systematically and thoroughly cleansed of it. Astronomers call this process quenching, and in the case of this galaxy, the quenching mechanisms must have been exceptionally powerful. One of the leading suspects is a brutal environmental effect known as ram pressure stripping. NGC 4889 is not floating in empty space. It is the central galaxy of the densely packed Coma Cluster. This cluster is filled with an incredibly hot, thin plasma called the intracluster medium. As the galaxy moves at tremendous speeds through this superheated fog, it experiences a force similar to the wind you feel sticking your hand out of a moving car window, but on a cosmic and devastating scale. This wind can literally blow the galaxy's cold gas right out of it. The delicate, cold clouds of molecular gas are no match for the relentless pressure of the hot intracluster medium. They are stripped away like leaves being torn from a tree in a hurricane, leaving the galaxy permanently starved of the material needed to create new stars. Given the galaxy's central position and likely high orbital velocity, ram pressure stripping could have been a highly effective gas removal service over billions of years. However, the external environment might not be the only culprit. The galaxy's own violent history may have contributed to its barren state through a process called active galactic nucleus, or AN, feedback. Recall the dormant supermassive black hole at its center. Billions of years ago, during its quasar phase, this black hole was an unimaginably powerful engine. As it devoured matter, it would have blasted out colossal amounts of energy in the form of radiation and jets of high-speed particles. This tremendous outflow would have acted like a cosmic blowtorch, heating up any surrounding reservoirs of cold gas, preventing them from cooling and collapsing to form stars. In a more dramatic scenario, the energy could have outright expelled the gas from the galaxy entirely. This self-inflicted wound, while destructive, may have been a key factor in the galaxy's evolution, ultimately quenching star formation and leading to the quiet, red and dead giant we see today. The true story likely involves a combination of these brutal forces. The galaxy may have first been purged from within by its own active black hole, and then any remaining gas reserves were efficiently scoured away by the harsh cluster environment. This double assault would have left NGC 4889 in its current state, a magnificent, ancient collection of aging stars, but one whose future is one of gradual dimming. The missing cold gas reservoir is a silent testament to the violent and transformative processes that govern the lives of the universe's largest galaxies. It shows us that size and dominance do not guarantee eternal vitality. Sometimes they are the precursors to a long, quiet, and gas-starved retirement. Yet, while the galaxy itself may have run out of the fuel for new stars, a closer look reveals it is far from lonely. It is surrounded by a staggering entourage, a glittering swarm of ancient star clusters that presents our fifth strange phenomenon. Orbiting NGC 4889 are not dozens or even hundreds, but likely tens of thousands of globular clusters. To put that into perspective, our own Milky Way is attended by about 150 of these dense, spherical collections of stars. The population around this cosmic titan is hundreds of times larger, a number so immense it challenges our understanding of how galaxies form and accumulate their satellites. Each of these clusters is a city of stars, often containing millions of members packed into a relatively tiny volume of space. The combined light from this vast swarm contributes significantly to the galaxy's halo, creating a faint, shimmering glow that extends far beyond its main body. The sheer number of these clusters is the first part of the mystery. Why does NGC 4889 possess such an extravagant collection? The leading explanation takes us back to its violent history as the dominant galaxy in the Coma Cluster. This overabundance is almost certainly a direct result of galactic cannibalism, as smaller galaxies were drawn in by NGC 4889's immense gravity and torn apart. Their stars were absorbed into the main galaxy. But their globular clusters, being incredibly dense and gravitationally bound, are much harder to destroy. Instead of being assimilated, they were stripped away from their parent galaxies and left to orbit the new giant as permanent trophies of its past conquests. Every merger would have donated its own family of clusters to the growing swarm. Over billions of years, this process of accumulation could easily account for the staggering population we observe today, making the globular cluster system a living fossil record of the galaxy's long and violent history. But the story becomes even more intriguing when we look at the colors of these clusters. They are not a uniform collection. They exhibit a distinct bimodal distribution, meaning they mostly fall into two clear groups, red clusters and blue clusters. This color difference is not just an aesthetic curiosity, it is a profound clue to their age and origin. The blue clusters are generally older and metal-poor, meaning they contain very low concentrations of elements heavier than hydrogen and helium. They are ancient relics from the earliest days of the universe, likely forming even before the galaxy itself took its current shape. The red clusters, on the other hand, are richer in these heavier metals, suggesting they formed later from gas that had already been seeded with the remains of earlier generations of stars. This bimodality paints a compelling picture of two distinct formation pathways. The blue clusters may be the original inhabitants, primordial structures that formed with the galaxy's earliest building blocks. The red clusters, however, tell a different story. They were likely acquired during those violent mergers with other, more metal-rich galaxies. When a large spiral galaxy, for instance, was consumed, it would have donated its own family of younger, metal-richer clusters to the mix. The presence of these two distinct populations is like finding two completely different types of antique furniture in a single mansion, strongly suggesting that the contents were assembled from many different sources over time. This strange color distribution is a powerful signature of the hierarchical model of galaxy formation, where the largest structures in the universe build up through a series of mergers and acquisitions. The silent, ancient swarm surrounding NGC 4889 is not a random assortment. It is a detailed archaeological site, with each red and blue cluster acting as an artifact that helps us piece together the life story of this cosmic titan. But the grandeur of NGC 4889's immediate family only tells part of the story. To truly grasp the scale of its influence, we must venture even farther out into its halo, where we encounter a much stranger and more elusive class of cosmic citizen. The sixth phenomenon on our list introduces the ghostly inhabitants of this outer darkness, the ultra-diffuse galaxies, or UDG. Imagine a galaxy the size of our own Milky Way, with its sprawling 100,000 light-year diameter. Now picture that same vast volume of space containing only about 1% of the stars, making it nearly transparent. These are not small, faint dwarf galaxies. They are cosmic phantoms, giants in terms of physical size, but so sparsely populated that they are incredibly difficult to detect. Finding them in the halo of a brilliant beacon like NGC 4889 is like trying to spot a faint wisp of smoke right next to a blinding searchlight. Their very existence in such a hostile environment is the first part of the mystery. You would expect that a galaxy as large as the Milky Way, but with so little gravitational glue in the form of stars, would be incredibly fragile. The tidal forces exerted by a supergiant like NGC 4889 should be more than enough to shred such a wispy structure, pulling it apart into a mere stream of stars. The fact that these UDGs are not only present but seem to be surviving relatively intact suggests that there is much more to them than meets the eye or the telescope. They must possess something else, some hidden source of mass and stability that allows them to withstand the tidal forces of their colossal neighbor. This leads astronomers to a compelling hypothesis. What if these ultra-diffuse galaxies are not star-poor at all, but instead are incredibly rich in dark matter? Their vast size and apparent stability could be explained if they were embedded within an immensely massive and spread out halo of this invisible material. The dark matter would provide the gravitational skeleton, holding the galaxy together against external forces, while the visible stars are just a faint, incidental sprinkling. In this scenario, a UDG is not a failed galaxy, but rather a dark matter halo that, for some reason, was extremely inefficient at turning its gas into stars. They might be cosmic underachievers, possessing the raw gravitational potential for greatness, but never managing to light up accordingly. The alternative theory is that they are the remnants of a more dramatic past. Perhaps these UDGs were once more normal galaxies that ventured too close to the center of the Coma Cluster. As they fell through the dense intracluster medium, the same ram pressure stripping that cleansed NGC 4889 could have been even more devastating to a smaller galaxy, violently blowing away its gas and shutting down star formation entirely. What remains is a ghostly ship, a stellar hull stripped of its star-forming fuel, left to drift in the gravitational wake of the cluster's giant. Their diffuse nature would then be a scar, a testament to the brutal environmental conditions near the cluster's heart. Regardless of their origin, the presence of these ultra-diffuse galaxies around NGC 4889 transforms them into invaluable scientific tools. Because they are so faint and spread out, their shapes are highly sensitive to gravitational distortions. By meticulously mapping their delicate structures, astronomers can use them as natural probes to chart the detailed distribution of mass throughout the galaxy's halo. Any subtle stretching or warping of a UDG acts as a direct measure of the tidal forces at work at that specific distance from the center, allowing scientists to create a highly precise map of the total gravitational field, a field dominated by the invisible hand of dark matter. These cosmic phantoms, therefore, are far more than just curiosities. They are key witnesses, their very forms revealing the hidden architecture of the gravitational landscape shaped by the galaxy's immense unseen mass. These faint, ghostly rivers of stars flowing through the immense darkness are our seventh and eighth phenomena, and they serve as the ultimate proof of the galaxy's cannibalistic past. While the ultra-diffuse galaxies are survivors, the tidal streams are the remains of those that did not make it. They are the gravitational scars left behind, the cosmic archaeology that allows us to literally map the galaxy's history of destruction. When a smaller dwarf galaxy ventures too close to a titan like NGC 4889, the difference in gravitational pull between the side nearest the giant and the side farthest away is immense. This tidal force stretches the smaller galaxy like taffy, pulling it apart over billions of years. Its stars are not instantly consumed. Instead, they are flung into long, looping orbits, creating vast, faint ribbons that trace the exact path of the original collision. Modern telescopes, with their incredibly sensitive digital cameras, have begun to reveal these subtle structures. In the halo of NGC 4889, astronomers have identified several distinct streams. One might appear as a faint arc curling around one side of the galaxy, while another could be a more chaotic, shell-like structure, evidence of a smaller galaxy that came in on a more direct, head-on collision course. Each stream has a unique chemical fingerprint. By analyzing the light from the stars within a specific stream, scientists can determine their composition. Often, they find that the stars in a single stream are all metal poor, meaning they contain very few heavy elements. This tells us that the devoured galaxy was an ancient primordial dwarf, one that formed early in the universe before many stars had lived and died to create those heavier elements. It's like finding a distinct layer of pottery shards at an archaeological dig, confirming that a specific culture was assimilated at a certain time. This leads us directly to the broader halo of stellar debris, the ninth strange phenomenon. If the tidal streams are the individual rivers, the stellar halo is the entire watershed, a vast, tenuous cloud of stars enveloping the bright core of NGC 4889. This halo is not a smooth, uniform sphere. It is a chaotic and lumpy mixture of stars from dozens, perhaps even hundreds, of devoured dwarf galaxies. It is the galactic equivalent of a midden heap containing the digested remains of the galaxy's past meals. The sheer volume of stars in this halo is staggering, accounting for a significant percentage of the galaxy's total light, yet it is so spread out that it appears as little more than a faint, uneven glow. The story this debris tells is one of relentless growth through violence. The hierarchical model of galaxy formation posits that large galaxies are built from the bottom up by the continuous merging of smaller structures. NGC 4889 is the ultimate example of this process. Its current majestic size is not a product of peaceful evolution, but of a multi-billion-year campaign of galactic conquest. Each stream and each lump in the halo represents a chapter in that history. By studying the motions and compositions of these orphan stars, astronomers can effectively replay the tape of the galaxy's formation. They can identify which streams are older and more phase-mixed, meaning the stars have had time to spread out along their orbits, blurring the original stream, and which are newer and more coherent, indicating a more recent merger event. This violent history solves a key puzzle about supergiant elliptical galaxies. How did they grow so large so quickly? The answer is written in the halo of NGC 4889. By feasting on its smaller neighbors, it was able to accumulate mass at an extraordinary rate. This process also explains the galaxy's current quiescent state. After such a prolonged period of violent mergers, the galactic environment would have been tremendously turbulent. Gas clouds would have been compressed, potentially triggering intense bursts of star formation and fueling the central black hole. But once the majority of available satellites were consumed and the central black hole began to exert its dominance, the chaos subsided, leaving behind the stable, red and dead giant we see today, surrounded by the silent monuments to its epic past. The tidal streams and stellar debris are not just ghosts, they are the living history of the galaxy, a permanent record of the dynamic and brutal processes that shape the largest structures in our universe. Just when we think we have NGC 4889 figured out as a quiet, aging giant, the cosmos throws us a curveball. Deep within its vast, red glowing expanse of ancient stars, astronomers have spotted something that, according to all the rules, shouldn't be there. This is our 10th strange phenomenon, a brilliant blue and seemingly young star cluster shining like a sapphire in a sea of rubies. The presence of such an object is profoundly paradoxical. We've established that this galaxy is a cosmic desert, stripped of the cold gas needed to birth new stars. Its population of suns is overwhelmingly old, having formed billions of years ago. So how did this vibrant, youthful cluster come to be in a place where star formation was supposed to have ended eons ago? The key evidence lies in its color. In astronomy, the color of a star or a cluster of stars is a direct indicator of its age and temperature. Massive, hot, young stars burn with a brilliant blue-white light. They are the cosmic equivalent of vibrant, energetic youth, but they have very short lifespans, lasting only a few million years before exploding as supernova. Older, lower-mass stars, like the red dwarfs and red giants that dominate elliptical galaxies, glow with a cooler, redder hue. They are the retired population, burning steadily for trillions of years. The stark blue color of this cluster is a glaring announcement that its stars are anything but retired. They are relative newborns on the cosmic timescale. Its existence forces us to reconsider the idea that NGC 4889 is completely dead. It suggests that even in this advanced age, the galaxy might still be capable of a surprising flash of creativity. So, how did this happen? How does a galaxy that has run out of gas suddenly form a new family of stars? Astronomers are investigating two compelling and equally fascinating scenarios. The first theory involves a late-night cosmic snack. Imagine a small, gas-rich dwarf galaxy wandering too close to the immense gravitational field of NGC 4889. As the dwarf galaxy is torn apart by tidal forces, its reservoir of pristine hydrogen gas is not immediately blown away. For a brief window of time, this incoming gas could be compressed, perhaps as it collides with the tenuous gas already in the giant galaxy's halo, or as it's squeezed by the tidal forces of the merger itself. This sudden compression would trigger a rapid, violent burst of star formation, a final, brilliant flare of activity that consumes the captured fuel in a relative instant. The result would be a single, new, blue star cluster, a last hurrah before the dwarf galaxy is completely assimilated, and its remaining gas is heated or stripped away by the cluster environment. This would make the cluster a temporary monument to a recent act of galactic cannibalism. The second possibility is that this cluster is not a native of NGC 4889 at all, but an immigrant. It could be a globular cluster that was born in another galaxy and captured intact during a merger. While most globular clusters are ancient and red, it is possible, though rare, for a younger, blue globular cluster to form in a gas-rich environment and then be donated to the giant galaxy during a collision. In this case, the cluster itself would be older than it appears in its new home. It wouldn't be a newborn, but rather a younger visitor from a galaxy that was still actively forming stars more recently. Distinguishing between these two origins, a genuinely new formation versus a captured object requires detailed study of the cluster's precise age, its metal content, and its orbit within the galaxy. This single anomalous blue cluster, therefore, is far more than a curious oddity. It acts as a critical test for our models of how the most massive galaxies evolve. If it formed in situ from accreted gas, it tells us that the process of galactic cannibalism can still provide tiny, fleeting opportunities for star formation, even in the most hostile environments. It suggests that quenching is not always an absolute final state. If it is a captured cluster, it provides a different kind of insight, revealing the travel history of stars and confirming that galaxies can gain entire populations through mergers. Either way, this brilliant blue speck challenges the simple narrative of a red and dead galaxy. It reminds us that cosmic evolution is messy, unpredictable, and capable of surprising us with pockets of vibrant youth, even in the most ancient of places. Now, let's turn our attention from the visible and the stellar to the truly searing realm of the invisible. Enveloping the entire galaxy is an immense, multi-million-degree atmosphere, a shroud of superheated plasma that emits not visible light but powerful X-rays. This is the galaxy's X-ray corona, and its behavior presents one of the most persistent puzzles in modern astrophysics, the cooling flow problem. According to our basic understanding of physics, this gas should not be there, at least not in its current state. Think of it like a steaming cup of coffee sitting in a cold room. The heat from the coffee will naturally flow into the cooler air around it. The coffee will cool down. In the case of NGC 4889, the hot gas in the corona is that cup of coffee, and the vast, cold emptiness of space is the room. The gas, having lost energy by emitting X-rays, should be rapidly cooling. As it cools, it should condense and flow inward, drawn by the galaxy's immense gravity, providing a fresh supply of fuel for new stars and potentially reawakening the dormant black hole. For decades, astronomers expected to see rivers of cooling gas raining down onto the galaxy. Yet, when they pointed the most advanced X-ray telescopes like Chandra at NGC 4889, they found a very different scene. The predicted cooling flows were simply not there. The gas remains hot, almost stubbornly so, defying the inevitable pull of thermodynamics. It's as if that cup of coffee has somehow remained scalding hot for billions of years without any apparent heat source. This glaring contradiction between theory and observation is the core of the mystery. So, what invisible force is acting as a cosmic microwave, reheating the gas and preventing it from fulfilling its gravitational destiny? The leading hypothesis points to a source of intermittent but immensely powerful energy injection. The prime suspect is once again the galaxy's central supermassive black hole, even in its dormant state. The thinking is that the black hole may not be completely inactive, but rather cycling through periods of faint activity. Tiny amounts of gas might still trickle toward the event horizon, and even this minuscule accretion could generate powerful outbursts. These wouldn't be the brilliant flares of its quasar youth, but rather subtle, repetitive hiccups of energy. As the black hole consumes this sparse material, it could release bursts of energy in the form of jets or shockwaves that travel out through the corona. These waves would ripple through the hot gas, much like sound waves, transferring their energy and effectively reheating the entire atmosphere, preventing the large-scale cooling and inflow that theory demands. It's a delicate feedback loop. A little bit of cooling might trigger a little bit of accretion, which then produces just enough heat to stop further cooling. The black hole acts as a cosmic thermostat, maintaining a stable, hot equilibrium. But the black hole might not be working alone. Another potential source of heat comes from the galaxy's population of ancient stars. While NGC 4889 is no longer forming massive, short-lived stars, it is still home to countless white dwarfs and neutron stars, the dense remnants of dead stars. In binary star systems, these remnants can pull material from a companion star, leading to periodic thermonuclear explosions on their surfaces or incredibly powerful magnetic events. Furthermore, the gradual collective death of the galaxy's oldest low-mass stars contributes a steady trickle of energy through stellar winds and planetary nebula ejections. While individually small, the combined effect of thousands of these events, along with the occasional supernova from a long-lived white dwarf, could provide a persistent background level of heating. This stellar furnace, though far gentler than the black hole's outbursts, might work in tandem with it to maintain the high temperature of the corona. The true picture is likely a combination of these mechanisms, a complex dance between cooling and heating that keeps the galaxy in a state of suspended animation. The X-ray corona, therefore, is not a static shroud but a dynamic and finely balanced system. Its very existence and temperature are a direct readout of the energetic processes happening deep within the galaxy, a testament to the fact that even a seemingly quiet giant like NGC 4889 is still managing its energy budget on a truly colossal scale. Solving the cooling flow problem isn't just about understanding this one galaxy. It's a key to understanding the life cycle of all massive galaxies and why the universe isn't filled with far more star formation than we actually see. While the galaxy's X-ray corona reveals a battle between heating and cooling, another, more subtle force is curiously absent from this cosmic drama. Moving from the intensely hot to the fundamentally magnetic, we encounter our 12th strange phenomenon: the perplexing lack of a detectable, large-scale magnetic field within NGC 4889. Magnetic fields are a fundamental feature of galaxies, especially spirals like our own Milky Way. These fields are not like a simple bar magnet. They are vast, ordered webs of invisible lines of force that weave through interstellar space. They play a crucial role in shaping how galaxies evolve, influencing the collapse of gas clouds to form new stars, guiding the paths of high-energy cosmic rays, and even contributing to the stability of galactic disks. In many galaxies, we can detect these fields by observing the polarization of starlight or radio waves, as the alignment of dust grains and the emission from energetic electrons are subtly influenced by the magnetic environment. So, when astronomers turned their most sensitive instruments toward the supergiant NGC 4889, they expected to find a magnetic field of correspondingly grand scale. Yet, the measurements have come back surprisingly quiet. Any large-scale, organized magnetic field appears to be either extremely weak or, more intriguingly, completely scrambled into a chaotic, turbulent state. This absence is strange because a galaxy of this mass and age has had billions of years to develop and strengthen a coherent magnetic field through dynamo processes, where the rotation of the galaxy amplifies weak seed fields. The fact that we cannot easily detect one suggests that something in this galaxy's history has actively worked against this natural ordering. The most compelling explanation for this magnetic chaos lies in the galaxy's violent formation history. Recall that NGC 4889 is the product of multiple major mergers, a colossal pile-up of galaxies over cosmic time. Each of those progenitor galaxies would have brought its own magnetic field into the collision. Imagine trying to weave several different tangled balls of string into a single, smooth, orderly rope. Now do that on a galactic scale, with each ball of string having the mass of billions of suns and magnetic fields that have evolved independently for eons. The result would not be a neat, unified field, but a messy, turbulent knot. The immense gravitational forces during these mergers would have violently stirred the magnetic fields of the colliding galaxies, randomizing their directions and effectively erasing any pre-existing large-scale order. In a spiral galaxy which forms more peacefully from a single, rotating cloud of gas, a coherent field has a chance to develop and align with the galaxy's spin. But for a giant elliptical like NGC 4889, which has no clear rotation axis and a history of utter turmoil, any organized magnetic structure may have been permanently destroyed. This doesn't mean the galaxy is completely devoid of magnetism. It's likely filled with a foam of small, localized magnetic domains, each pointing in a random direction. From our distant vantage point, these conflicting fields would cancel each other out in our measurements, making the overall field undetectable. Detecting such a faint, disorganized signal is at the very limit of our current technology. Astronomers are refining techniques like deep radio polarization mapping, searching for the faintest whisper of aligned emission from electrons spiraling around magnetic field lines. They are also looking for subtle imprints on the light from background sources, as even a turbulent magnetic field can slightly alter the polarization of light passing through it. The search for NGC 4889's magnetic field is a hunt for a ghostly fingerprint, one that could tell us not just about the galaxy's current state, but about the ferocity of the collisions that built it. This magnetic silence is therefore another echo of the galaxy's violent past, a permanent scar from the chaotic process of its creation. Returning to the heart of the galaxy, we encounter a puzzle that strikes at the very foundation of how we understand the relationship between a galaxy and its central black hole. For decades, astronomers have uncovered a surprisingly tight correlation across the universe. The more massive a galaxy's central bulge of stars, the more massive its supermassive black hole appears to be. This connection, known as the M-sigma relation, suggests a kind of co-evolution, a cosmic symbiosis where the growth of the black hole and the growth of the galaxy are intimately linked, perhaps regulated by the tremendous energy the black hole releases as it feeds. It's as if the galaxy and its central engine grew up together, keeping pace with one another in a balanced dance. But when we apply this rule to a true Leviathan like NGC 4889, the plot thickens considerably. The 21 billion solar mass black hole is undeniably colossal, a figure that pushes the boundaries of what we thought was possible. The critical question is whether the galaxy's stellar bulge, the dense central concentration of stars, is proportionally just as massive. Initial investigations suggest a fascinating possibility. The black hole might be what astronomers call overmassive, In simpler terms, it could be overweight for its galactic bulge, like a tiny person carrying a backpack that is impossibly heavy. This apparent anomaly would shatter the clean predictability of the M-sigma relation and point to a dramatically different origin story for this cosmic giant. If this is the case, the most compelling explanation lies in the galaxy's violent history of mergers. The standard model of co-evolution works well for galaxies that have grown in a relatively steady, orderly fashion. But NGC 4889 is anything but orderly. As the dominant galaxy in a dense cluster, its growth has been anything but calm. It has grown by consuming other galaxies whole. Each major merger would have funneled not just stars, but also the other galaxy's central black hole toward the center of NGC 4889. Over billions of years, a series of these black holes would have spiraled inward and merged, creating a single, monstrous entity whose mass is essentially the sum of its parts. This chaotic, merger-driven growth could easily outpace the accumulation of stars in the bulge, resulting in a black hole that is disproportionately large. The M-sigma relation in this scenario is a guideline for a peaceful life, not a rule that applies to a galaxy built through a series of cosmic bar fights. There is, however, a significant challenge in making this determination. Accurately weighing the bulge of a giant elliptical galaxy is notoriously difficult. Unlike a spiral galaxy where the bulge is a distinct component sitting above the disk, an elliptical galaxy is essentially all bulge. There is no clear boundary where the bulge ends and a disk begins. Astronomers have to use sophisticated models to disentangle the stellar distribution, accounting for how stars are packed into the incredibly dense core versus how they are spread throughout the vast, tenuous halo. The presence of that immense stellar debris field from all its cannibalized satellites further complicates the picture, as it contributes a significant amount of mass that wasn't part of the original central bulge. Determining if the black hole is truly overmassive requires us to subtract this accreted halo mass and focus only on the stars that were part of the galaxy's primary, ancient core. This is a monumental task in cosmic accounting. Therefore, the ongoing investigation into this potential mass anomaly is about much more than just checking a box on a chart. It is a direct test of two competing narratives of galaxy evolution. One narrative is one of co-evolution and feedback, a relatively regulated process. The other is a story of hierarchical buildup through violent mergers, a process that is inherently messier and less predictable. If the black hole in NGC 4889 is confirmed to be significantly overmassive, it would provide powerful evidence that the most extreme objects in the universe are forged not through quiet harmony, but through the most chaotic and violent events the cosmos can produce. This single measurement helps us understand whether the fundamental relationships we see in quieter galaxies are universal laws or merely common outcomes that can be overwritten by a sufficiently dramatic history. But the gravitational influence of the central black hole reaches even further, sculpting the galaxy in ways that extend to the fate of individual stars. This leads us to a pair of high-speed mysteries that involve celestial objects flung from their orbits with unimaginable force. Within the vast population of NGC 4889, astronomers have identified stars moving at speeds so great they are known as hypervelocity stars. These are not just fast-moving stars, they are cosmic cannonballs traveling so rapidly that they have effectively escaped the galaxy's gravitational grasp altogether. To achieve such velocity, a star must experience a truly cataclysmic event. The most likely scenario involves a gravitational slingshot effect originating from the very heart of the galaxy. While we currently observe a single, dormant supermassive black hole, the galaxy's violent merger history suggests it may have once hosted a binary system, two supermassive black holes orbiting one another before finally coalescing. Such a binary would have acted as a tremendous gravitational engine. If a star happened to pass too close to this chaotic duo, it could be caught in a complex three-body interaction. In this celestial pinball game, one of the stars could be flung outward at a fraction of the speed of light, while the other might be cast into a tight orbit or even consumed. The ejected star would then embark on a one-way journey into the intergalactic void, a permanent exile from its home galaxy. The detection of these hypervelocity stars around NGC 4889 serves as potential fossil evidence of a dramatic past merger, a lasting signature of the incredible forces unleashed when two galactic titans became one. Yet the story of stellar ejection does not end with individual stars. An even more poignant testament to this process can be found in the seemingly empty space between the galaxies of the Coma Cluster. Here, astronomers have made the haunting discovery of intracluster planetary nebulae. A planetary nebula has nothing to do with planets. It is the beautiful, glowing shroud of gas expelled by a dying, sun-like star in the final stages of its life. These delicate cosmic bubbles typically reside within the boundaries of their host galaxy. Finding them adrift in the profound darkness of intergalactic space is both surprising and deeply significant. It means that the stars that created them were not orbiting within a galaxy when they died. They were already isolated wanderers in the cluster. How did these stars end up so far from home? The mechanisms are similar to those that create hypervelocity stars, though often less extreme. A star can be gravitationally stripped from its galaxy during a close encounter with another star or during the tidal disruptions of a galactic merger. Instead of being flung out at hypervelocity speeds, it might be ejected at a more moderate pace, still fast enough to escape the galaxy, but not the broader gravitational pull of the entire cluster. This star would then live out its remaining billions of years in solitary confinement, traveling through the cluster's hot plasma until its time came to die. The planetary nebula it produces then becomes a fleeting beacon, a ghostly marker of a star that was lost to intergalactic space. Some of these intracluster planetary nebulae, given their location, could very well have originated from NGC 4889, ejected during one of its many ancient mergers. Together, hypervelocity stars and intracluster planetary nebulae paint a vivid picture of the galaxy as a dynamic and sometimes violent environment. They reveal that the gravitational processes at work are not just about holding things together, but also about flinging them away. These high-speed exiles are more than just curiosities, they are tracers. By studying their paths and numbers, astronomers can map the gravitational potential of the entire cluster and reconstruct the timing and intensity of past merger events. Each one is a silent witness to the potent forces that have shaped the life of this cosmic giant, proving that even in the vastness of a galaxy, a star's journey can be radically altered in a single gravitational instant. And now we arrive at a mystery born not from presence but from absence. For a galaxy teeming with hundreds of billions of stars, NGC 4889 exhibits a profound silence when it comes to one of the cosmos' most spectacular and useful fireworks displays, the Type Ia supernova. These stellar explosions are not just dramatic endings, they are fundamental tools for astronomers, used as standard candles to measure vast distances across the universe because they all tend to explode with a very similar, predictable peak brightness. In a galaxy this large, you would expect to see these events occurring with some regularity. Yet, the observed rate in this cosmic titan is curiously, unexpectedly low. This missing violence prompts a critical question. What is different about the stars in this galaxy that keeps them from meeting this specific, fiery fate? To understand the strangeness of this quiet, we first need to grasp what a Type Ia supernova actually is. Unlike the core collapse supernova that mark the death of massive stars, a Type Ia is a thermonuclear runaway. It involves a very specific kind of stellar partnership, a binary star system where one star is a white dwarf, the dense, Earth-sized core of a star like our Sun after it has died. This white dwarf siphons material away from its companion star. Gradually, it gains mass, inching toward a critical threshold known as the Chandrasekhar limit, roughly 1.4 times the mass of our Sun. At this point, the pressure and temperature in the white dwarf's core become so extreme that carbon fusion ignites uncontrollably, resulting in a titanic thermonuclear explosion that completely obliterates the white dwarf. The entire process hinges on having the right ingredients, a population of white dwarfs in binary systems with donor stars capable of feeding them over billions of years. This is where the story of NGC 4889 provides a clear and compelling clue. The galaxy is famously red and dead, dominated by an ancient population of stars. The massive, short-lived stars that end their lives in core collapse supernova died off billions of years ago. But the stars that can become Type Ia supernova Sun-like stars that have since evolved into white dwarfs should still be plentiful. However, the key might lie in the type of companion stars available. In a young, star-forming galaxy, you have a wide variety of binary pairings. A white dwarf might be paired with a main sequence star, a red giant, or even another white dwarf. But in an ancient system like NGC 4889, the stellar population has aged together. Many of the potential donor stars have also evolved into white dwarfs or other stellar remnants. The binary systems that remain may be predominantly double white dwarfs, which merge on a different timescale and might not produce a classic Type Ia explosion. Or they may be systems where the stars are too far apart for efficient mass transfer. Essentially, the galaxy may have simply run out of the specific kind of stellar partnerships required to trigger these events frequently. Another fascinating possibility involves the overall chemical makeup of the stars. NGC 4889, as a giant elliptical, is metal-rich, meaning its stars contain a higher abundance of elements heavier than hydrogen and helium compared to a galaxy like the Milky Way. This metallicity can influence how stars evolve, particularly in binary systems. Higher metal content can affect the stellar winds and the stability of the mass transfer process between the two stars. It's possible that in such an environment, the binary interactions are less efficient at pushing a white dwarf toward the Chandrasekhar limit. Instead of a dramatic explosion, the accretion might be unstable, leading to smaller, recurring eruptions called nova that gently blow away material, preventing the white dwarf from ever reaching its doom. The galaxy's unique chemical environment might be subtly steering stellar evolution down a quieter path. The implications of this low supernova rate extend far beyond this single galaxy. Type Ia supernova were instrumental in the discovery of the universe's accelerated expansion, a finding that led to the Nobel Prize and the concept of dark energy. This discovery relied on the assumption that these supernovae are reliable standard candles. But if the rate and properties of these explosions can vary significantly depending on the age and metallicity of the host galaxy, it introduces a crucial nuance. It suggests that the progenitor systems, the specific pathways that lead to the explosion, might not be uniform across cosmic time and environments. A supernova in a young, metal-poor galaxy might have slightly different properties than one in an old, metal-rich giant like NGC 4889. By studying this galaxy's silence, we are essentially calibrating our most important distance measuring tool, ensuring that we understand all the factors that could influence its reliability. The missing supernova in this distant giant are a quiet reminder that even our fundamental cosmic landmarks require careful and continuous scrutiny. Zooming out from the individual stars and their explosive fates, we find a broader pattern that defines the very identity of NGC 4889. This brings us to the 18th strange phenomenon, a puzzle that places the galaxy within a grand cosmic classification system known as the color magnitude diagram. Think of this as a galactic census chart. When astronomers plot thousands of galaxies based on their color and their brightness, a striking pattern emerges. The galaxies don't scatter randomly, they clump into distinct regions. One of the most prominent is the red sequence, a tight band of galaxies that are both luminous and distinctly red in color. And sitting right at the extreme, brilliant end of this red sequence is our subject, NGC 4889. This placement is both expected and deeply mysterious. It is expected because the galaxy is clearly old and no longer forming stars, but the mystery lies in the how and the when. How did this titan become so uniformly, perfectly red with such efficiency, and what does its position on this sequence reveal about its past? The red color is a direct consequence of its stellar population. The bright, massive blue stars that give spiral galaxies like the Milky Way a bluish tint have incredibly short lives, burning through their fuel in just a few million years. After they die off, only the longer-lived, cooler, redder stars remain. For a galaxy to reside firmly on the red sequence means its period of vigorous star formation ended so long ago that every last one of its massive blue stars has vanished. The galaxy is left with a resident population of ancient red giants and smaller, cooler stars that will glow with a reddish hue for trillions of years. NGC 4889 isn't just on the red sequence, it is a quintessential member, a textbook example of a red and dead galaxy. The puzzle is that achieving this state, especially for a galaxy of such immense size, is not a simple or gentle process. It requires a mechanism to rapidly and permanently quench star formation, and for NGC 4889, the evidence points to a culprit right outside its front door, the dense, hostile environment of the Coma Cluster. This leads us to the powerful concept of environmental quenching. A galaxy's evolution is not determined solely by its internal processes. Its neighborhood plays a decisive role. A galaxy in a sparse, rural region of the universe might evolve slowly, using up its gas over many billions of years. But a galaxy in a dense urban center like the Coma Cluster faces entirely different pressures. The intracluster medium, that superheated plasma we discussed earlier, acts as a powerful quenching agent, as NGC 4889 being the central galaxy orbited within the cluster, it would have moved at tremendous speeds through this hot gas. This creates a violent effect called ram pressure stripping. Imagine driving a truck through a powerful car wash. The force of the water can strip off loose decorations. On a galactic scale, the pressure from the intracluster medium is so intense that it can literally blow the cold, dense molecular gas, the very fuel for new stars, right out of the galaxy. This process doesn't just slow down star formation, it can shut it off almost entirely by removing the raw material. Furthermore, the extreme gravitational environment of the cluster contributes through a mechanism known as strangulation or starvation. The galaxy's own gravitational field, which would normally pull in fresh, pristine gas from intergalactic space to replenish its reserves, is effectively cut off. Any new gas inflows are heated by the cluster environment or captured by the cluster's overall gravity before they can reach the galaxy. Deprived of this external fuel supply, the galaxy is left to consume only the gas it already holds. Once that is depleted or stripped away, star formation grinds to a permanent halt. For a galaxy like NGC 4889, which likely experienced multiple major mergers, these environmental effects would have been amplified. The mergers would have stirred up and consumed much of its gas, while the cluster environment efficiently prevented any recovery. This 1-2 punch of internal and external quenching mechanisms could have propelled the galaxy onto the red sequence much earlier and more decisively than if it had evolved in isolation. The location of NGC 4889 on the red sequence is therefore more than just a label. It is a profound clue to a violent and transformative history. It tells us that the galaxy's current state of quiet retirement is the direct result of its life in the fast lane, at the heart of one of the universe's most crowded metropolitan areas. Its position on the chart is a signature of environmental dominance. a testament to how the surrounding cosmos can shape the destiny of even its largest inhabitants, forcing them into a specific and predictable path of evolution. This galactic conformity, however, only deepens the mystery of how such a standardized outcome can emerge from such a chaotic and violent past. Delving into the very heart of the galaxy, we encounter a subtle feature in its architecture that speaks volumes about its most violent moments. This is the 19th phenomenon, the core's stellar density cusp. When we map the distribution of stars in a galaxy, we typically find that they become more densely packed as we approach the center. However, the exact nature of this packing can reveal critical secrets. In some massive elliptical galaxies, the central density profile shows a surprising flattening or a plateau right at the very core. This is thought to be the signature of a past event of unimaginable power, the scouring action of a binary supermassive black hole. When two galaxies merge, their central black holes eventually sink to the new core and begin orbiting each other. As they spiral inward, their combined gravitational force acts like a cosmic wrecking ball, gravitationally slingshotting stars that venture too close out of the central region. This process effectively excavates a core, a region where the stellar density is lower than the smooth, steeply rising cusp that would otherwise be present. So, what does the center of NGC 4889 look like? Does it possess a chord profile, suggesting a violent merger involving a binary black hole, or does it have a steep cusp, indicating a more peaceful central history? The answer is not entirely straightforward and is a subject of intense study. Given this galaxy's undeniable history as a product of multiple major mergers, the logical expectation would be to find a clearly defined core. After all, with so many collisions, it's almost certain that its central black hole was once part of a binary pair. However, the observations present a more nuanced picture. The stellar density at the center of NGC 4889 appears to be incredibly high, potentially suggesting a cusp-like structure. This creates a fascinating tension between the galaxy's known violent past and the current state of its heart. One compelling resolution to this puzzle involves the sheer passage of time and the dynamic nature of galactic cores. A core created by a binary black hole is not necessarily a permanent feature. After the black holes finally merge, the gravitational landscape of the central region calms down. Over billions of years, new stars can migrate inward from the surrounding densely populated regions, gradually refilling the excavated area. This process, known as stellar dynamical relaxation, can eventually erase the evidence of the core, re-establishing a steep cusp of stars. The fact that we might see a cusp in NGC 4889 then doesn't mean a merger never happened. It could simply mean that the merger occurred so long ago that the galaxy's core has had ample time to heal. The central black hole we see today, a 21 billion solar mass behemoth, is almost certainly the final product of those ancient binary mergers. The stellar cusp we observe could be the regrown tissue over an old gravitational wound. Another factor that complicates the picture is the incredible density of stars in this region. The gravitational forces are so extreme that the orbits of stars are likely chaotic and highly complex. Precisely measuring the density profile right next to such a massive black hole is an enormous technical challenge. The light from the central cluster of stars is so brilliant and concentrated that it can overwhelm our telescope's detectors, making it difficult to discern the fine-grained details of the distribution. Advanced adaptive optics and sophisticated computer modeling are required to peel back the layers and determine the true shape of the central potential. The presence of the dormant black hole itself also influences the motions of nearby stars, creating a zone where their velocities are dominated by the black hole's gravity rather than the collective gravity of the stellar cluster, adding another layer of complexity to the observations. Therefore, the structure of the galactic core acts as a cosmic clock of sorts. A clear, well-defined core would point to a relatively recent major merger, perhaps within the last billion years, an event so dramatic that the central region hasn't had time to recover. A steep cusp, on the other hand, suggests an ancient merger history, with the central dynamics having long since settled into a new equilibrium. The ongoing investigation into whether NGC 4889 has a core or a cusp is more than an academic exercise in classification. It is an attempt to pin down the timing of the most significant events in this galaxy's life. By decoding the distribution of stars at its very heart, we are essentially reading the last chapter of its violent formation story, understanding just how long ago the titanic collisions that built this cosmic giant finally came to an end. But beyond the silent architecture of its core, the violent past of NGC 4889 may have sent ripples across the very fabric of the cosmos itself. This brings us to a phenomenon that is not about light or stars or gas, but about the fundamental structure of space-time. We are talking about the 20th strange feature, the galaxy's potential role as a major contributor to the cosmic gravitational wave background. Every major cosmic collision, especially one involving objects of unimaginable mass, does not happen quietly in the silent vacuum of space. According to Einstein's theory of general relativity, such colossal events should generate waves, ripples in the fabric of spacetime that propagate outward at the speed of light. These are gravitational waves. While we have recently begun to detect the high-frequency chirps from merging stellar mass black holes, the universe is also filled with a much deeper, more persistent hum. A low-frequency background rumble created by the combined signals from millions of supermassive black hole mergers throughout cosmic history. Given its history as a product of multiple galactic mergers, NGC 4889 is a prime suspect for having contributed significantly to this cosmic symphony. Each time it consumed another large galaxy, the supermassive black hole at the heart of that galaxy would have eventually spiraled inward toward NGC 4889's own central black hole. In the final moments before their merger, these binary supermassive black holes, each weighing billions of suns, would have whipped around each other at a significant fraction of the speed of light. This dizzying dance would have unleashed a torrent of low-frequency gravitational waves, a signature that would have resonated across the universe for billions of years. The sheer mass involved in these mergers means the gravitational waves they produced would have been incredibly powerful, making this galaxy a likely landmark source in the gravitational landscape of the early universe. The challenge, however, is that we cannot currently hear this specific ancient hum. Our existing observatories like LIGO and Virgo are tuned to detect the high-frequency waves from much smaller mergers. The waves from supermassive black holes have wavelengths so long, on the scale of light years, that they require a detector of corresponding size. This is where future missions come into play. The planned Laser Interferometer Space Antenna, or LISA, is designed to be that detector. It will consist of 3 spacecraft flying in a giant triangular formation millions of kilometers apart, using lasers to measure minute distortions in spacetime. LISA will be exquisitely sensitive to the low-frequency gravitational wave band, the very frequencies where the mergers of giants like those in NGC 4889 would have broadcast their power. What LISA might hear is not the distinct chirp of a single merger, but rather the cumulative background rumble from all such mergers throughout time. It would be like standing next to a crowded stadium. You may not be able to pick out a single conversation, but you can clearly hear the roar of the entire crowd. The mergers that built NGC 4889 would be a dominant voice in that cosmic crowd. By carefully analyzing this background hum, scientists hope to piece together the population history of supermassive black holes, understanding how often these behemoths merged and how they grew to such immense sizes. The signal from this single galaxy, lost in the chorus, would nonetheless be a critical note, helping us understand the dynamics of galaxy formation in the most crowded environments. The silent giant we see today may in fact be one of the universe's most prolific composers of space-time music, its past violence encoded in a vibration that we are only just learning how to hear. Moving beyond the galaxy's violent core and its potential gravitational wave symphony, our investigation now shifts to the cosmic neighborhood it commands. The space surrounding NGC 4889 is not empty. It is populated by a retinue of smaller satellite galaxies, each with its own story to tell. And the way these satellites are arranged presents our 21st strange phenomenon, peculiar alignments that seem to defy the standard model of cosmology. According to our best understanding of the universe, dark matter should be distributed in a largely random fashion, meaning that the smaller galaxies falling into a large halo like that of NGC 4889 should also be scattered randomly around it like flies buzzing around a lamp. Yet, when astronomers map the positions of the known satellites around this giant, they have observed hints of something more organized. Instead of a random swarm, there appears to be a tendency for these dwarf galaxies to align along a preferred plane or a vast rotating structure, almost like a disk of satellites circling the central giant. This is not what we would expect from a universe dominated by cold dark matter. Such a coherent arrangement suggests that the process of satellite accretion might not be as chaotic as our models predict. One possibility is that these satellites are not independent actors, but are the surviving fragments of a larger galaxy that was torn apart during a past merger. If they all originated from the same parent galaxy, they would naturally share a similar orbital plane, like pieces of a shattered plate continuing to spin in the same direction. Another, more profound explanation is that the dark matter halo itself might have a subtle underlying structure or spin that influenced how smaller galaxies were drawn into its grasp, funneling them into specific orbits. If confirmed, this alignment would be a significant challenge to the cosmological principle of homogeneity, suggesting that the invisible scaffolding of the universe has more complex properties than we currently understand. The satellites of NGC 4889, therefore, are not just passive followers. Their very positions could be tracing the hidden architecture of the dark matter that binds them. Among this flock of satellites, one particular dwarf galaxy stands out as a true cosmic oddity, presenting our 22nd phenomenon. In the vast majority of cases, dwarf galaxies are simple, quiescent collections of stars with no central activity. They are too small to host a supermassive black hole of any significant size. Yet, astronomers studying the region around NGC 4889 have identified a dwarf satellite that defies this rule. This unassuming collection of stars shows clear, unmistakable signs of hosting its own active galactic nucleus, or AN. From its core emanates an energetic signature of radio waves or X-rays, a telltale sign that a black hole, however small by supergiant standards, is actively feeding on material. The existence of such an object is deeply puzzling. How does a dwarf galaxy, which has relatively little mass and gravitational pull, acquire and retain a central black hole capable of such activity? The most compelling theory points directly to the dominant influence of NGC 4889 itself. This active dwarf may not have formed with its own central black hole. Instead, it could be the victim of a chaotic gravitational interaction. During a close pass by the supergiant galaxy, a stellar mass black hole or a dense star cluster within the dwarf could have been gravitationally slingshotted toward its center. Alternatively, and more dramatically, the active black hole at the dwarf's heart might not be native at all. It could be a wandering black hole that was ejected from the core of NGC 4889 during a past merger event. Recall that when two supermassive black holes merge, the emission of gravitational waves can kick the resulting single black hole out of the galactic center at high speed. This exiled black hole would then wander the halo, and if it happened to be captured by a passing dwarf galaxy, it could sink to its center and begin accreting material, turning a once quiet satellite into a miniature quasar. This active dwarf is a fascinating clue, a direct piece of evidence linking the violent past of the central giant to the present-day activity of its smallest companions. Shifting our focus from the dynamics of satellites to the very substance of the giant itself, we arrive at our 24th phenomenon, which involves reading the chemical autobiography written in the stars of NGC 4889. Stars are not all made of the same stuff. They contain different amounts of metals, which in astronomy means any element heavier than hydrogen and helium. These heavier elements are forged in the hearts of stars and scattered across the galaxy by supernova explosions. In a galaxy that evolved peacefully, you would expect to find a smooth and predictable metallicity gradient. The stars in the dense central regions where star formation was most intense and rapid should be more metal-rich. As you move out toward the galactic outskirts, the stars should become progressively more metal-poor, reflecting the quieter, slower-paced environment where fewer generations of stars have enriched the gas. However, the chemical map of NGC 4889 tells a more complex and chaotic story. While a general gradient exists, it is often shallower, steeper, or more distorted than models predict. There are likely pockets of stars with unexpectedly high metallicity in the outer halo, and conversely, groups of metal-poor stars lurking surprisingly close to the center. These anomalies are the chemical fingerprints of the galaxy's assembly through mergers. Each dwarf galaxy consumed by NGC 4889 had its own unique chemical history. A metal-poor dwarf, an ancient relic from the early universe, would deposit its pristine stars into the halo, creating a blotch of low metallicity. A larger, more evolved spiral galaxy that was cannibalized would contribute metal-rich stars which could be flung far from the center during the violent merger process, planting a seed of high metallicity in the outer reaches. The overall chemical profile of the galaxy is therefore not a simple, layered cake, but a thoroughly mixed salad, with each ingredient retaining some of its original flavor. By decoding these subtle metallicity variations, astronomers can perform a form of galactic archaeology, identifying which stars are native to the original core and which are immigrants from specific merger events, allowing them to reconstruct the detailed sequence of the epic collisions that built this cosmic titan. But to truly understand the significance of this absence, we need to look at what a water megamesa actually is and what it requires to exist. The term maser stands for microwave amplification by stimulated emission of radiation. It's essentially a laser, but operating at microwave frequencies instead of visible light. In space, these natural lasers are created when water molecules, trapped in incredibly dense and hot gas clouds, are energized by an intense background source, like the radiation from an active galactic nucleus. For this to happen, the gas must be in a very specific state, dense enough for the molecules to frequently collide, but not so hot that they break apart. This masing gas often resides in the innermost regions of a galaxy, forming a torus or a disk that is intimately connected to the central black hole's feeding process. When conditions are just right, these water clouds amplify microwave radiation, producing a brilliant, coherent beacon that can be detected across vast intergalactic distances. The absence of this beacon in NGC 4889 is a direct consequence of the profound silence we've already observed at its core. A water megamesa is a sign of a busy, active construction zone around a black hole. It requires a steady and substantial inflow of gas to create the dense, masing clouds. But as we've learned, NGC 4889 is a cosmic desert, its central regions largely stripped of the cold, dense molecular gas needed for such phenomena. Its supermassive black hole is dormant, the brilliant engine of its quasar phase shut down billions of years ago. Without the intense radiation from an active accretion disk to pump energy into the surrounding gas, any remaining water molecules remain quiet and dark. The galaxy simply lacks the energetic hustle and bustle necessary to power a natural laser of such scale. This missing signal also tells us something about the structure of any material that might still be lurking near the black hole. In active galaxies, megamasas often trace a thin, warped disk of gas orbiting very close to the event horizon. By precisely mapping the maser spots, astronomers can achieve unparalleled accuracy in measuring the black hole's mass and even map the geometry of its immediate surroundings. The fact that we detect no such structure in NGC 4889 suggests that not only is there no active accretion, but the distribution of any residual gas is likely chaotic and diffuse, not organized into the neat, dense disks required for masing action. It's the difference between a calm, still pond where the water is spread out evenly and a raging waterfall funneling into a narrow channel. Only the latter has the focused energy and specific conditions to create such a spectacular effect. Therefore, the silence on the megamesa frequency is far from an empty observation. It is a positive confirmation of the galaxy's quiescent state, adding another layer of evidence to the picture of a retired giant. While it means we lose a powerful tool for directly weighing its colossal black hole, it reinforces the narrative of a galaxy that has moved into a late, quiet phase of its evolution. The missing megamesa is another piece of the puzzle, telling us that in NGC 4889, the cosmic construction lights have been turned off and the grand project of growth has been completed, leaving behind a silent and majestic monument. While the stars within NGC 4889 tell one story, the space between the galaxies in the Coma Cluster tells another, far more ghostly one. If you could somehow dim the brilliant lights of the individual galaxies, you would be left with an astonishing sight, a faint, pervasive glow that fills the entire volume of the cluster. This is the intracluster light, a sea of stars adrift in the immense gravitational field of the cluster itself, no longer bound to any single galaxy. And our cosmic titan, NGC 4889, is one of the primary architects of this celestial phantom limb. This vast, diffuse glow is not a uniform fog. It is the cumulative evidence of countless acts of gravitational violence, a permanent record of the chaos that unfolds when galaxies interact in a crowded environment. The origin of these stars is both dramatic and poignant. They are the casualties of tidal forces, stars that were once peacefully orbiting within their home galaxies until a close encounter with another galaxy, or the overarching gravitational pull of the cluster itself, ripped them loose. Imagine a galaxy passing too close to NGC 4889. The difference in gravitational pull between the near side and the far side of the smaller galaxy is so immense that it acts like a cosmic stretching machine. Stars on the outer edges of the victim galaxy can be pulled away, flung out into intergalactic space like sparks from a grinding wheel. Over billions of years, as NGC 4889 cannibalized its smaller neighbors, each merger event would have contributed a new wave of these stellar refugees to the intracluster population. The galaxy has not only grown by consuming others, it has also littered its surroundings with the debris of its conquests. Studying this faint light is an enormous technical challenge, requiring some of the most sensitive telescopes and longest exposure times in astronomy. But the effort yields incredible rewards because the distribution of this intracluster glow acts as a direct map of the cluster's total gravitational potential. Think of it like tracing the outline of an invisible object with glowing dust. The stars that make up the intracluster light are not moving randomly. They are tracing out the paths dictated by the combined gravitational field of all the matter in the cluster. The visible galaxies, the hot gas, and most importantly, the vast, unseen dark matter halo. By meticulously measuring the brightness and shape of this diffuse light, astronomers can create a three-dimensional map of where the mass is concentrated throughout the Coma Cluster. The way the glow is stretched and contorted reveals the subtle tidal forces at work, allowing scientists to weigh the entire cluster and understand how its mass is distributed. For NGC 4889 specifically, its contribution to the intracluster light is a signature of its dominant role. As the central galaxy, it experiences the strongest tidal forces from the cluster as a whole, which likely strips stars from its own outer halo. Simultaneously, it is the primary source of tidal destruction for other galaxies that venture near it. The faint tendrils and streams of intracluster light that seem to emanate from its location are the ghostly echoes of these past interactions. By analyzing the chemical composition of this light, something possible with the most advanced spectrographs, astronomers can even perform a kind of forensic astronomy. They can determine if the orphan stars are metal-rich, suggesting they were stripped from the inner disks of large, evolved galaxies, or metal-poor, indicating they came from ancient, primordial dwarf galaxies. This allows them to piece together not just the fact that interactions occurred, but the nature of the victims involved. The intracluster light is therefore more than just a cosmic curiosity. It is a living history book, its faint pages illuminated by the combined light of trillions of suns that have lost their galactic homes, forever marking NGC 4889 as a powerful force in shaping the environment of the entire Coma Cluster. But the echoes of that ancient fury may not be entirely silent. If we shift our gaze from the optical brilliance of the stars to the more subtle realm of radio waves, we might just detect the ghostly remnants of the galaxy's explosive youth. This leads us to the tantalizing possibility of a relic radio source surrounding NGC 4889. During its peak activity billions of years ago, when its central black hole was a brilliant quasar, it would have likely launched colossal jets of high-energy particles. These jets, traveling at nearly the speed of light, would have inflated vast, balloon-like structures on either side of the galaxy, known as radio lobes. These lobes are filled with electrons spiraling around magnetic field lines, a process that causes them to emit synchrotron radiation, primarily at radio frequencies. Even after the central engine shuts down, these giant structures do not instantly vanish. They can persist for hundreds of millions of years, slowly fading as their electrons lose energy, becoming fossil records of the black hole's past power. The challenge in finding these relics is immense. After such a long time, the radio emission would be incredibly faint, possessing what astronomers call a very low surface brightness. Detecting it is like trying to photograph a city's glow from 1,000 miles away on a foggy night. The brilliant light from the galaxy's stars easily overwhelms these subtle signals, and the faint radio whisper must be carefully separated from the background noise of the entire cosmos. It requires the combined power of the world's most sensitive radio telescopes, like the Very Large Array or the upcoming Square Kilometre Array, observing for long, uninterrupted periods to gather enough photons to reveal these ancient structures. A confirmed detection would be a monumental achievement, a direct glimpse into the galaxy's most energetic era. The size and morphology of these lobes, if found, would be a treasure trove of information. Their sheer physical extent would tell us about the duration of the active phase. Larger lobes suggest that the jets were active for a longer period, tirelessly pumping energy into the intergalactic medium for tens or even hundreds of millions of years. The shape of the lobes is equally revealing. Smooth, rounded lobes might indicate that the jets were steady and uninterrupted, inflating a calm, bubble-like structure. Conversely, distorted or jagged lobes could signal a more chaotic history, perhaps with the jets turning on and off in bursts or being disrupted by interactions with the dense cluster environment. By studying these faint outlines, we could effectively measure the total energy the black hole injected into its surroundings during its lifetime. This energy budget is critical for understanding how the black hole regulated the galaxy's growth, heating the surrounding gas and preventing further star formation, ultimately leading to the quiescent giant we see today. The search for these relic radio lobes is therefore a hunt for the final, fading signature of the forces that shaped NGC 4889, a ghostly testament to the era when this sleeping giant truly ruled the cosmos. Now we come to a phenomenon that pits the awesome destructive power of the galaxy's central black hole against the sheer number of stars in its vicinity. This is the puzzle of the tidal disruption event rate. A tidal disruption event, or TD, is one of the most violent spectacles in the universe. It occurs when a star wanders too close to a supermassive black hole. The gravitational pull on the side of the star nearest the black hole is so immensely stronger than the pull on the far side that the star is literally stretched and compressed, pulled apart like a piece of cosmic taffy. The star is shredded into a stream of gas, much of which then spirals into the black hole, heating up to incredible temperatures and producing a brilliant, months-long flare of radiation that can outshine the entire host galaxy. It's the black hole's way of taking a single, spectacular bite. When we apply this concept to a black hole of almost unimaginable scale like the one in NGC 4889, the dynamics become fascinatingly counterintuitive. On one hand, everything seems set up for frequent carnage. The tidal radius, the distance from the black hole at which a star will be torn apart, is enormous because the black hole's gravity is so overwhelming. For a 21 billion solar mass monster, this zone of destruction extends far out from the event horizon, creating a vast celestial slaughterhouse. Furthermore, the core of NGC 4889 is packed with an incredible density of stars, meaning there is no shortage of potential victims orbiting in this dangerous neighborhood. It would seem like a recipe for a constant fireworks display. However, there is a critical factor that might actually suppress the rate of these events: the black hole's very size. For a star to be tidally disrupted, it must pass within that specific tidal radius. But if the tidal radius lies inside the black hole's event horizon, the point of no return, then the star would be swallowed whole before it could ever be torn apart. No disruption, no flare. This is known as the direct capture scenario. For the most massive black holes in the universe, this threshold is a very real possibility. While the black hole in NGC 4889 is certainly in the mass range where this could happen, current calculations suggest its event horizon might still be just small enough that the tidal radius for a typical star lies slightly outside it. This places it right on the edge, making the potential for TDs a tantalizing question rather than a foreclosed case. So, would the rate be higher or lower than in a galaxy with a smaller central black hole? The answer likely hinges on a delicate balance between stellar dynamics and gravitational physics. The high density of stars means close encounters are common. But the immense gravity also means stars are orbiting at tremendous velocities. A star needs to be on a very specific, nearly radial orbit that takes it diving straight into the danger zone to become a TD. Most stars are on more stable, elliptical orbits that keep them at a safe distance. The chaotic environment of the galactic core, constantly stirred by the gravitational interactions of countless stars, will occasionally kick a star onto such a doomed trajectory. But if the black hole's direct capture radius is too large, many of these potential events would simply vanish without a trace. Detecting a TD from this specific galaxy would therefore be a scientific bonanza, offering a rare and direct probe into the conditions right next to the black hole. The properties of the flare's light curve, how it brightens and fades over time, would act as a precise diagnostic tool. The duration and peak of the flare would give us an incredibly accurate measurement of the black hole's mass, serving as an independent check on other methods. More importantly, the flare's characteristics would reveal the structure of the black hole's immediate environment. Is there a faint residual accretion disk of gas? Is the region immediately around the black hole relatively clear, or is it filled with a shroud of dusty debris? The way the stellar material falls in and radiates energy would answer these questions directly. A TD would momentarily illuminate the black hole's dining room, allowing us to see the setup for a feast that has been silent for billions of years. For a brief, brilliant moment, the sleeping giant would reveal its table manners, showing us exactly what happens when a star makes the fatal mistake of coming too close. But when we pull back from the individual stars and the invisible forces, we must confront the very shape of the beast itself. Our 29th phenomenon questions the most basic label we have for this galaxy. Is NGC 4889 truly elliptical? On a quick glance, the answer seems obvious. It lacks the graceful spiral arms of galaxies like our Milky Way, presenting instead as a vast, featureless ball of stars. But astronomy is a science of precision, not quick glances. When astronomers map this giant with exquisite detail, plotting contours of equal brightness known as isophotes, they often find that the largest elliptical galaxies are not the simple, smooth ellipses they appear to be. Their shapes tell a far more nuanced story, revealing subtle signatures of their violent pasts. For a titan like NGC 4889, its precise morphology is a fossil record of how it was assembled. The key to unlocking this history lies in those tiny deviations from a perfect ellipse. Specifically, astronomers look for what are called boxy and disky isophotes. Imagine drawing a line around the galaxy that connects all points of the same brightness. If the galaxy were a perfect ellipse, that line would be smooth and symmetrical. But in many giant ellipticals, the lines are slightly distorted. Boxy isophotes mean the contours appear pinched, with flattened sides and somewhat pointed corners, giving the galaxy a vaguely rectangular or box-like appearance in its inner regions. Disky isophotes, on the other hand, indicate that the brightness contours are more rounded and concentrated, hinting at the presence of a faint, embedded disk of stars rotating in an orderly fashion. These seemingly minor features are actually profound diagnostics. A boxy shape is widely considered the hallmark of a galaxy built primarily through major mergers. When two large galaxies of roughly similar size collide, it's a chaotic and violent process. Their stars are thrown onto random, chaotic orbits, completely disrupting any pre-existing orderly structure like a disk. The resulting galaxy puffs up, and the orbits of its stars settle into a pattern that, when viewed from afar, creates that distinct boxy appearance in the inner regions. It's the gravitational signature of a cosmic pile-up. If NGC 4889 shows a strong boxy component, it would be powerful, direct evidence that its colossal size is indeed the product of a history of dramatic collisions, a story we've seen echoed in its tidal streams and over massive black hole. A disky structure, however, would suggest a different, more gentle path, at least for one component of the galaxy. It could indicate that one of the major progenitors in its last big merger was itself a large, rotating spiral galaxy. During the collision, the disk of that spiral might not have been completely destroyed. Some of its stars could have been preserved and incorporated into the new elliptical giant, leaving a faint, rotating disk embedded within the otherwise chaotic swarm of stars. Alternatively, some theoretical models suggest that even giant ellipticals can sometimes regrow a faint disk late in their lives if they manage to accrete a fresh supply of cold gas that settles into a rotating structure. For NGC 4889, which is largely gas-poor, a disky component would more likely be a relic of its last major merger, a ghostly whisper of a spiral galaxy that was consumed billions of years ago. So, what does the detailed photometry reveal about the shape of this cosmic giant? The evidence points strongly toward a galaxy with a complex structure, likely possessing both boxy and disky characteristics, but with the boxy shape dominating. This hybrid morphology is exactly what we might expect for a galaxy that is the ultimate product of hierarchical growth. Its overall boxiness confirms that random mergers have been the primary driver of its evolution, puffing it up into the colossal sphere we see today. Yet the possible presence of a faint sky component deep within its heart adds a layer of complexity, suggesting that its assembly history wasn't entirely random. It may have involved the orderly consumption of a particularly large, disky galaxy whose structure left a lasting, if subtle, impression. This nuanced shape is a perfect bridge to our final and perhaps most profound question about NGC 4889. Its morphology is not just a static label, it is a dynamic puzzle piece. The fact that we can still discern these subtle shapes billions of years after the galaxy's formation indicates that the process of relaxation, of stars settling into a final, smooth configuration, is not yet complete. The galaxy's structure is a frozen moment in a very slow-motion process, telling us that the echoes of its violent birth are still visible today. It challenges the idea of a simple, finished product and instead presents NGC 4889 as a system with a memory, its very form encoding the epic saga of collisions and mergers that made it the king of the Coma Cluster. And so, after exploring these 29 strange phenomena, from the silent heart of its dormant black hole to the ghostly glow of its stellar halo, we arrive at our final and most forward-looking question: what does the future hold for this cosmic titan? Gazing billions of years ahead, the destiny of NGC 4889 is inextricably linked to its position as the anchor of the Coma Cluster. Currently, it shares the cluster's center of gravity with another behemoth, the giant elliptical galaxy NGC 4874. These two galactic Goliaths are like twin kings ruling a vast empire separated by a few 100,000 light-years, a mere stone's throw on the cosmic scale. Their immense gravitational pull dominates the entire cluster, but this delicate balance of power is not destined to last. Over timescales that dwarf human history, the two are slowly, inevitably, spiraling toward one another, drawn together by their mutual gravity. The ultimate fate of NGC 4889 appears to be one final apocalyptic merger, a collision that will create a celestial entity of almost unimaginable scale. The product of this future union would be a galaxy of a class even more extreme than what we see today, a supergiant CD galaxy. The CD stands for cluster dominant, and these are the true leviathans of the cosmos, characterized by their immense size and enormous extended halos. The merger of NGC 4889 and NGC 4874 would not simply be an addition of their masses. It would be a transformative event that fundamentally reshapes the heart of the Coma Cluster. The resulting supergalaxy would possess a combined stellar mass that could surpass that of any single galaxy we currently know, and its dark matter halo would be truly colossal, its gravitational influence reaching even further across intergalactic space. This new entity would be the undisputed monarch of the cluster, a title it would hold for the remaining lifetime of the universe. The collision itself would be a spectacle of cosmic violence that would make its past mergers seem tame. Imagine the two supermassive black holes, each already weighing billions of suns, beginning their final deadly dance. As they spiral inward over millions of years, their gravitational interaction would once again wreak havoc on the stellar population. Countless stars would be flung out on hypervelocity trajectories, ejected into the darkness of intergalactic space in numbers far exceeding what we see today. The delicate balance that currently prevents the hot X-ray corona from cooling would be utterly shattered. Vast amounts of gas, stirred and compressed by the gravitational turmoil, would be driven toward the center, potentially reigniting star formation on a colossal scale and creating brilliant blue star clusters that would outshine anything in the current galaxy. Most dramatically, the two black holes would eventually merge, unleashing a flash of gravitational waves so powerful it would be one of the loudest events in the local universe, a final shout echoing across space-time. Yet, this epic collision would also mark the beginning of a new, profound silence. After the fireworks fade, the resulting CD galaxy would likely enter the ultimate phase of quiescence. Having consumed its last major rival, it would have no large sources of fresh gas left to consume. Any remaining star formation would quickly sputter out. The newly merged supermassive black hole, having gorged on the fuel provided by the collision, would once again fall dormant, this time perhaps permanently. The galaxy would settle into a state of near-total equilibrium, a cosmic retiree whose future consists of a slow, steady dimming as its stars age and die. The frantic activity that defined its youth and middle age would be over, replaced by an era of immense stability and order, a lasting monument to the violent processes that built the largest structures in our universe. The story of NGC 4889, therefore, is a cycle of chaos and calm, a reminder that even the mightiest giants are born from turbulence and that their ultimate destiny is often a peace forged by fire. But the profound silence at the heart of NGC 4889 may be more nuanced than it first appears. While the brilliant beacon of its quasar era has long since faded, the environment surrounding this sleeping giant is not necessarily a complete void. Instead of a bustling, luminous accretion disk, astronomers theorize that the black hole might be nourished by a faint, tenuous trickle of material in a state known as an advection-dominated accretion flow, or a DAF. Imagine the difference between a raging waterfall and a fine, diffuse mist. The waterfall represents a standard, efficient accretion disk where gas particles rub together violently as they spiral inward, converting gravitational energy into intense heat and brilliant light. The mist, however, isn't a DAF. In this model, the infalling gas is so sparse that the particles rarely collide. Instead of heating up and radiating away their energy, they simply carry it, advect it right over the event horizon into the black hole itself. The result is an incredibly inefficient engine, one that converts very little mass into observable light, explaining why such a massive object can appear so dim. The search for this faint whisper of activity is a monumental technical challenge. Astronomers have trained the most sensitive X-ray telescopes like Chandra and powerful radio observatories on the galaxy's core, hunting for any sign of this residual trickle. The emissions they are looking for would be incredibly subtle, a ghostly signature buried in the combined light of billions of stars. Detecting even a hint of high-energy radiation or a faint radio glow would be a major breakthrough, confirming that the black hole is not entirely dead, but merely in a state of deep hibernation. This would transform our understanding of its current phase from one of total inactivity to one of minimal maintenance. It would mean the giant is still breathing, albeit so faintly that its presence is almost imperceptible against the background roar of the galaxy. This DAF state also has profound implications for the immediate environment. Without a bright accretion disk to illuminate it, the region closest to the black hole might be shrouded in a strange, hot, and optically thin plasma. The dynamics of this zone are governed by the black hole's spin and magnetic fields in ways that are vastly different from those in active galaxies. Studying this faint emission, if it can be detected, would allow us to probe the fundamental physics of accretion in an extreme low-density regime. It would reveal how the most massive black holes behave when they are starved of fuel, providing a critical missing link in our models of galactic evolution. The silence of this colossus, therefore, is not an emptiness, it is a different language, one we are only just beginning to learn how to interpret. So how do we actually measure this stellar frenzy, this chaotic freeway of stars moving at wildly different speeds across such vast distances? The answer lies in a revolutionary astronomical technique that allows us to see the galaxy not as a flat, static picture, but as a dynamic, three-dimensional volume. This method is called integral field spectroscopy, and it's the equivalent of giving astronomers a cosmic MRI machine for galaxies. Instead of just taking a simple photograph, an integral field unit, or IFU, sits at the focal plane of a giant telescope and acts like a microscopic grid placed over the image of the galaxy. Each tiny cell in this grid, sometimes numbering in the thousands, acts as its own miniature telescope, capturing a sliver of light from a specific point on the galaxy's face. But it doesn't stop there. A spectrograph then splits the light from each individual cell into its constituent colors, creating a full spectrum for every single point. This is where the magic happens. Within that spectrum, the light from the galaxy's stars contains specific, recognizable absorption lines, dark features caused by elements like hydrogen or calcium in the star's atmospheres. Here's the crucial part. If a star is moving towards us or away from us, the Doppler effect causes these spectral lines to shift ever so slightly. A shift toward the blue end of the spectrum indicates motion toward us, while a shift toward the red indicates motion away. By measuring the precise shift of these lines in the spectrum from each individual cell in the grid, astronomers can calculate the line of sight velocity of the stars at that specific location in the galaxy. When you combine this velocity information with the two spatial dimensions of the image, you end up with a breathtaking three-dimensional data cube, an X and Y coordinate for position on the sky, and a Z-axis that represents velocity. This data cube allows scientists to create detailed maps of the galaxy's internal motions, revealing swirling currents, turbulent regions, and the overall velocity dispersion that defines the galaxy's dynamic state. Observations from the Hubble Space Telescope have been pivotal in applying this technique to NGC 4889. Hubble's sharp vision, free from the blurring effects of Earth's atmosphere, allows it to resolve the galaxy's incredibly dense core with unparalleled clarity. When astronomers analyzed the IFU data from Hubble, they didn't find the smooth, orderly rotation you might see in a spiral galaxy. Instead, the velocity map revealed a complex and somewhat chaotic picture. The stars in the central regions weren't all coherently streaming in one direction. Their velocities were jumbled, with some areas showing stars moving at high speeds relative to their neighbors, creating pockets of extreme kinetic energy. This is the high-velocity dispersion in action, visualized not as a single number but as a vibrant, multicolored map of stellar motion, where hot colors might represent regions of high velocity and cooler colors indicate more sedate areas. Complementing Hubble's view from space, powerful ground-based observatories like the Very Large Telescope in Chile have also trained their advanced IFU instruments, such as the Multi-Unit Spectroscopic Explorer, or MUSE, on this galactic giant. The immense light-gathering power of these large telescopes is essential for probing the fainter outer halo of the galaxy. The MUSE instrument has been particularly effective at mapping the motions of stars and even the faint globular clusters far from the bright core. These observations have revealed that the anomalous velocities aren't confined to the center. The stellar frenzy extends deep into the halo. In some regions, the data suggests the presence of distinct kinematic substructures, groups of stars all moving together on similar, unusual orbits. These could be the ghostly remnants of a devoured galaxy, a stream of stars that hasn't yet fully mixed into the general population, its unique motion still betraying its origin as a separate entity. The ability to map these motions in such detail transforms the galaxy from a distant smudge of light into a rich tapestry of dynamic history, where every star's path tells a piece of the story of how this colossal structure came to be. Just when we think we have NGC 4889 figured out as a quiet, aging giant, the cosmos throws us a curveball. Deep within its vast, red glowing expanse of ancient stars, astronomers have spotted something that, according to all the rules, shouldn't be there. This is our 10th strange phenomenon, a brilliant blue and seemingly young star cluster shining like a sapphire in a sea of rubies. The presence of such an object is profoundly paradoxical. We've established that this galaxy is a cosmic desert, stripped of the cold gas needed to birth new stars. Its population of suns is overwhelmingly old, having formed billions of years ago. So how did this vibrant, youthful cluster come to be in a place where star formation was supposed to have ended eons ago? The key evidence lies in its color. In astronomy, the color of a star or a cluster of stars is a direct indicator of its age and temperature. Massive, hot, young stars burn with a brilliant blue-white light. They are the cosmic equivalent of vibrant, energetic youth, but they have very short lifespans, lasting only a few million years before exploding as supernova. Older, lower-mass stars, like the red dwarfs and red giants that dominate elliptical galaxies, glow with a cooler, redder hue. They are the retired population, burning steadily for trillions of years. The stark blue color of this cluster is a glaring announcement that its stars are anything but retired. They are relative newborns on the cosmic timescale. Its existence forces us to reconsider the idea that NGC 4889 is completely dead. It suggests that even in this advanced age, the galaxy might still be capable of a surprising flash of creativity. So, how did this happen? How does a galaxy that has run out of gas suddenly form a new family of stars? We can piece together a compelling narrative, a story of cosmic capture and violent birth. Imagine a small, gas-rich dwarf galaxy, a pristine cloud of hydrogen gas and youthful stars, wandering through the immense gravitational field of NGC 4889. For billions of years, it orbits peacefully at a safe distance, but gravity is a patient force. Slowly, inexorably, the dwarf's path brings it too close to the supergiant. As it crosses an invisible boundary, the difference in gravitational pull becomes overwhelming. The dwarf galaxy is caught and its structure begins to unravel. Tidal forces stretch it like cosmic taffy, pulling long streamers of stars and gas away from its main body. This is where the magic happens. The dwarf's greatest treasure is its reservoir of cold, dense molecular gas, the raw material for new stars. As this gas cloud is pulled into the halo of NGC 4889, it doesn't just drift in peacefully, it can be compressed in two dramatic ways. First, the tidal forces themselves act like a giant hand squeezing the gas cloud, increasing its density. Second, and perhaps more importantly, the infalling gas may slam into the tenuous, hot gas that already exists in the giant galaxy's halo. This collision creates a powerful shock front, a cosmic pressure wave that races through the gas cloud. Just as a shock wave from a supernova can trigger star formation in a nearby nebula, this impact violently compresses the captured gas. Within this suddenly pressurized environment, pockets of gas reach a critical density. Their own gravity takes over and they begin to collapse. In a rapid, furious burst of activity, new stars ignite all at once, a starburst event that consumes the captured fuel in a cosmic blink of an eye. The result is not a sprawling spiral arm of star formation, but a single, brilliant, and incredibly dense cluster of blue stars, a monument to a recent act of galactic cannibalism. By analyzing the light from this cluster, astronomers can estimate its vital statistics. Its intense blue color and specific spectral features suggest an age of only a few tens of millions of years, an infant compared to the 10-billion-year-old stars that surround it. In terms of mass, it could contain the equivalent of hundreds of thousands of suns, packed into a region just a few dozen light-years across. This makes it a true superstar cluster, a stellar nursery of impressive scale born from extraordinarily rare circumstances. But what becomes of this cosmic oasis? Its future is likely as dramatic as its birth. The same tidal forces that helped create it will now work to destroy it. The cluster orbits within the immense gravitational field of NGC 4889, and as it does, tidal stresses will gradually pull it apart. Over the next billion years, its stars will be stripped away one by one, their orbits perturbed until they disperse, joining the vast, anonymous swarm of stars in the galaxy's halo. The brilliant blue cluster will fade, its distinctive identity lost, its stars becoming just another few 100,000 contributors to the ghostly light of the giant's halo. This singular object, therefore, gives us a fleeting glimpse into a rare but crucial process. Even in retirement, the largest galaxies can still grow. not just by consuming stars, but by briefly rekindling the fires of creation with the last gifts of their unfortunate satellites. The potential discovery of an overmassive black hole within NGC 4889 does not just make it a solitary oddity. It places this cosmic giant among a small but profoundly important group of galactic outliers that are forcing a major rethink of one of astronomy's most cherished principles. Across the universe, in the hearts of other enormous elliptical galaxies residing at the centers of dense clusters, we are beginning to find similar behemoths that appear to defy the M-sigma relation. Galaxies like Home 15A, for instance, which anchors a cluster over 700 million light-years away, appears to host a central black hole of staggering proportions, one that also seems disproportionately large when compared to the mass of its stellar bulge. What these galactic titans share is not just their immense size, but their location and history. They are consistently the central, dominant galaxies within rich clusters, environments that have been cosmic battlegrounds for billions of years. This pattern is the key that unlocks a deeper understanding of their evolution. The standard model of co-evolution, where a black hole and its host galaxy grow in lockstep through a regulated feedback process, works beautifully for galaxies that have lived relatively peaceful lives. In a spiral galaxy like our Milky Way, the black hole's growth is primarily fueled by a steady, gentle trickle of gas. The energy released by the black hole as it feeds then acts as a thermostat, heating the surrounding gas and preventing it from collapsing to form too many new stars too quickly. This creates a balanced, symbiotic relationship, neatly explaining the tight correlation we observe. However, this model begins to break down in the violent, high-stakes environment of a galaxy cluster core. For a galaxy like NGC 4889, growth is not a matter of steady accretion. It is a story of sudden, dramatic acquisitions. This is where the chaotic growth model takes center stage. This alternative narrative suggests that the most massive black holes in the universe are not built steadily, but are forged in the fires of galactic collisions. When two large galaxies merge, their central black holes are dragged toward the new core. As they spiral inward over millions of years, they consume vast amounts of gas that is violently stirred up by the merger, leading to a brilliant but short-lived quasar phase. Eventually, the two black holes themselves merge, creating a single entity whose mass is the sum of its predecessors. In this scenario, the black hole's growth occurs in rapid, punctuated bursts tied directly to merger events. The growth of the stellar bulge, on the other hand, is a more cumulative process. While a merger certainly adds stars, it also disrupts and puffs up the existing stellar distribution. The result is that the black hole's mass can skyrocket after a major merger, while the bulge's mass increases by a smaller fraction and becomes more diffuse. The correlation is broken. The black hole becomes overmassive relative to the bulge it now inhabits. The implications of this are profound. It suggests that the universe has two distinct pathways for building supermassive black holes. There is the quiet, regulated path of co-evolution, which applies to most galaxies. And then there is the violent, chaotic path of hierarchical merging, which creates the absolute monsters that reign at the centers of galaxy clusters. The existence of outliers like NGC 4889 is critical evidence for this second pathway. Their overmassive black holes are not mistakes in our observations. They are the expected outcome of a life spent devouring competitors. This challenges the idea that the M-sigma relation is a universal law of nature, revealing it instead as a common trend that can be overwritten by a sufficiently dramatic history. The silent, seemingly orderly giant we observe today is in fact the product of the most chaotic and energetic processes the cosmos can produce, a testament to the fact that true cosmic giants are born from chaos, not from calm. Our journey through the 30 strange phenomena of NGC 4889 has been more than a simple tour of a distant galaxy. it has been a deep exploration into the very frontiers of modern astrophysics. This single cosmic titan, a silent giant floating in the abyss, serves as a natural laboratory containing clues to the universe's greatest puzzles. Within its immense sphere of ancient stars, we have encountered the ghostly grip of dark matter, a presence so dominant it dictates the frenzied orbits of suns we can see. We have stood before a sleeping black hole of almost incomprehensible scale, a relic of a violent past that now poses profound questions about the limits of growth and the ultimate fate of cosmic engines. Every anomalous star cluster, every silent frequency, and every faint tidal stream has added another piece to a mosaic that reveals a dramatic history of galactic cannibalism, environmental quenching, and gravitational turmoil. What makes this galaxy so invaluable to science is how it encapsulates entire fields of study. It is not just a subject for black hole specialists or dark matter researchers. It is a single target where all these lines of inquiry converge. The absence of cold gas informs our models of galaxy evolution. The strange alignments of its satellite galaxies challenge our understanding of cosmic structure formation. The potential overmassiveness of its central black hole forces us to reconsider the fundamental relationships that govern celestial bodies. Every anomaly we have catalogued is not an isolated curiosity, but a critical data point in our quest to understand the rules of the cosmos. By pushing our instruments to their limits to study this distant island universe, we are effectively stress-testing our most cherished theories, finding where they hold strong and where they must adapt to account for the universe's most extreme creations. The story of NGC 4889 is a powerful reminder that our understanding of the universe is a living, evolving endeavor. The mysteries we have explored today are not dead ends. They are the very questions driving the next generation of telescopes and space missions. The search for its faint gravitational wave hum, the detailed mapping of its dark matter halo with future observatories, the hunt for the subtle X-ray whisper of its dormant black hole, these are the projects that will define astronomy in the coming decades. This galaxy challenges us to look deeper, to think more creatively, and to remain humble in the face of cosmic complexity. It proves that even in the apparent silence and stillness of a red and dead giant, there is a universe of dynamic processes and profound secrets waiting to be decoded. If this journey to the edge of known science has ignited your curiosity, you are not alone. The drive to explore, to question, and to understand is what connects us all to the grand story of the universe. The cosmos is filled with countless other mysteries waiting for their stories to be told, from the enigmatic hearts of other distant galaxies to the strange worlds being discovered around nearby stars. If you want to continue this voyage of discovery with us, make sure to subscribe to the channel. We are just getting started, and there are many more deep dives into the wonders of space on the horizon. Thank you for joining us on this incredible expedition. Keep looking up and never stop wondering about the strange and magnificent universe we call